Hello and welcome back to Gradient Daily. We're here to give you a deep 15-minute dive into one of the most interesting AI papers out there. Today we've got something special from MIT by Tianhong Li and Kaiming He called Back to Basics, Let Denoising Generative Models Denoise. And this paper asks a really provocative question: what if the entire field of diffusion models took a wrong turn a few years ago? It argues that by going back to the simplest, most intuitive idea, we can build models that are not only more powerful, but way more efficient. So here's how we're going to break this down. First, we'll get into something called the denoising paradox. Then we'll use a really cool analogy, a trail on a mountain, to understand the core idea. After that, we'll meet the hero of the story, a model called JIT, or Just Image Transformers. We'll look at the incredible results to see why simple is better. And finally, we'll wrap up with some critique and what this all means for the future of AI. All right, first up, let's talk about this paradox. You'd think a denoising generative model would, denoise things. It's right there in the name. The whole idea is to take a noisy mess and clean it up. But somewhere along the line, the most successful models, the ones that power everything, they stop doing that. It's a really wild idea when you stop and think about it. Let's dig in. Okay, so look at this. The goal seems super obvious, right? On the left, you've got this image of a parrot that's been buried in noise. It's pretty much just static. And on the right, you've got the original clean picture. The job should be to get from A to B. But here's the crazy part. The models that we all know and love, like the ones behind Stable Diffusion, they don't actually do this. They took a completely different and way less intuitive path. And that's the big question this paper tackles. The original idea, the one that makes perfect sense, was to predict X, the clean image. But then a landmarked paper called DDPM came along and completely flipped the script. It showed that you got way better results if you predicted epsilon, the noise you added in the first place. It worked so well that it became the industry standard almost overnight. Then other models started predicting V, or velocity, which is kind of like predicting the GPS route from the noisy image back to the clean one. The whole field just decided it was better to predict these weird, indirect things, even though the final goal was always the clean image. So let's just lock in these terms, because they're going to be important. We've got X prediction, which is just guess the clean picture. Then there's epsilon prediction, which is guess the static we added, and V prediction, which is guess the path back to clean. Now here's the kicker. Mathematically, you can convert any one of these into the others with some pretty simple algebra. So for a long time, everyone just thought, it doesn't really matter which one you pick. But this paper argues that for the network that's actually doing the learning, it matters a lot. So why is it such a huge deal? To really get it, we need to zoom out and talk about a beautiful concept in machine learning called the Manifold Hypothesis. Trust me, this is a fantastic way to visualize what's going on and why predicting noise is such a hard problem. Okay, so imagine the space of all possible pixel combinations is this enormous, sprawling mountain range. It's just astronomically vast, and most of it is complete nonsense, just random static. But the tiny, tiny fraction of combinations that actually look like something, a person, a car, a landscape, they all live on these simple, well-defined trails that wind their way through the mountains. That collection of trails, that's the manifold of natural images. It's a simple structure in a ridiculously complex space. And here is where it all clicks. When you ask a model to do X prediction, you're basically asking it to learn the map of the trail. That seems manageable, right? But when you ask it to do epsilon prediction, you're dropping it somewhere random on the mountain and asking it to predict the exact vector pointing back to the trail. To do that, it has to kind of understand the entire chaotic mountain, not just the simple trail. So which task sounds easier for a network to learn? Mapping a simple path or mapping an entire mountain range? Now, this isn't just some cute analogy. The authors knew they had to prove it, so they designed this brilliant little toy experiment that makes the problem so obvious you can't ignore it. Okay, so check this out. They create a simple 2D spiral. That's our trail. Then they embed it in a higher dimensional space. Think of it like taking a flat drawing and projecting it into an 8-dimensional world. When the dimension is pretty low, like d equals 8, both methods do okay. The X prediction model learns the spiral, and the epsilon prediction model also figures it out. So far, so good. But look what happens when they crank that dimension all the way up to 512. The X prediction model on the left, it still nails it, a perfect spiral. It learned the simple trail. But the epsilon prediction model, it just completely falls apart into a noisy mess. It's a total disaster. It got hopelessly lost in the vastness of that 512-dimensional mountain. This, right here, is the smoking gun. This table basically just lays out all the different ways you could set this problem up. The columns are what the network predicts, and the rows are how you measure the error, or the loss. And what that little spiral experiment just showed us is that staying in that first column, making the network's job to predict X, is just way, way more stable when things get complicated and high-dimensional. Okay, so armed with this powerful insight, proven by that killer experiment, the authors went ahead and built a new model. And the name is just perfect, JET, which stands for Just Image Transformers. And when they say just, they really, really mean it. The model is just a standard off-the-shelf vision transformer. But here's the genius part. There's no fancy stuff, no complicated tokenizer, no pre-training on a billion images, no extra loss functions bolted on the side. It just takes big chunks of the noisy image, raw pixels, and its only job is to predict the clean version of that same chunk. That's it. It's X prediction, pure and simple.
And the process is exactly as simple as you'd think. During training, you take a clean image, you mess it up with noise, and you tell the network, hey, figure out what the original looks like. The one tiny little detail is that while the network predicts X, they found it's more stable to measure the error using V, that velocity term. And then to actually generate an image, you just start with a screen full of static and let the network clean it up step by step until the picture emerges. So, the big question. The theory is elegant. The toy experiment is convincing, but does this super simple back-to-basics idea actually work on a massive real-world dataset like ImageNet? Let's check out the results. And wow, the results are not just better, they are absolutely night and day. It is the spiral experiment all over again, but this time with real images. Look at this table. When they try to make the model predict noise or velocity, the model just breaks. The scores are terrible, it's a complete failure. But when they tell it to just predict the clean image, X, boom, really strong results. This isn't a small improvement. It's literally the difference between the model working and not working at all.
Okay, get ready for this next part because this is where it gets really wild. The researchers tried making the network less powerful. They added a bottleneck to squeeze the information down before it got to the main part of the model. Now, you think making the network dumber would hurt performance, right? Wrong. It actually made the model better. Think about that for a second. By forcing the model to compress the information, they were forcing it to ignore all the high-dimensional junk and focus only on learning the true, simple structure of the data, the manifold. Making the network weaker actually made it smarter.
So how does JIT stack up against the heavy hitters? Well, it achieves a state-of-the-art score. The image quality is right up there with the best of them. But here's the real kicker. Look at the pre-training column for JIT. It's empty. This model doesn't need a bunch of other complex models to prop it up. And now look at the compute column. It's way, way more efficient. It's achieving top-tier performance by being simpler, more direct, and computationally cheaper.
All right, so no paper is ever the final answer. Let's take a second to be critical here and talk about the strengths, the weaknesses, and what this all means for the future. So, on the plus side, the approach is just beautifully simple. It's elegant, it's efficient, and it works incredibly well. On the flip side, because it's so minimalist, it's probably not the absolute ceiling for performance. You could likely squeeze out even better scores by adding some of those extra tricks back in. It can also be a little finicky to tune, and this paper really only looks at class conditional generation, not the big text-to-image problem that everyone is focused on.
But here's why this paper is so exciting, and it goes way beyond just making pretty pictures. Think about science, protein folding, drug discovery, weather forecasting. In all of those fields, a huge challenge is just figuring out how to represent the data for an AI model. This approach just skips that step entirely. It works directly on the raw, messy, high-dimensional data. This could be a total game changer, a kind of foundational tool for generative AI in science.
All right, let's boil this whole thing down to 3 key takeaways. Number 1, trust the manifold. It's way easier to teach a model to learn a simple trail than it is to teach it to map an entire chaotic mountain. Number 2, simplicity is a superpower. A basic transformer, if you give it the right job, can be an incredibly powerful and efficient tool. And number 3, this is way bigger than just pixels. This back-to-basics idea could be a new playbook for building generative models for all kinds of scientific data. Hey, if you enjoyed this deep dive and learned something new, do us a favor and hit that like button and subscribe to Gradient Daily. We break down a fascinating new paper just like this one every single day. Thanks so much for watching, and we'll see you tomorrow.